I will now begin the presentation of the work Context-Aware Routing and Forwarding Model for NDN-based VANET by Elidio, Silva, Joaquim, Macedo, and Antonio Costa. This is the outline of our presentation. I will present an introduction, motivation, model design, and the summary and discussion of the contributions. This work aims at leveraging the characteristics of NDN on vehicular ad hoc networks, specifically NDN-based routing protocol and a forwarding strategy, both enhanced by mobility prediction and development. We present here the idea, and we do not have final results yet. Next slides briefly present the characteristics of VANET and the NDN. VANET is a specific case of VANET where, differently from VANET, the network is highly dynamic, which results in a highly intermittent network. And although the network is highly dynamic, the mobility in this network is very predictable because it's limited to the road topology. In addition, power and computational capabilities are not constraints in VANET. A special attention is given to this network due to its potential in improving the requirements for intelligent transportation system. Currently, VANET and its applications are mostly based on TCP/IP protocol stack, which still presents some challenges such as the host mobility, the network security, data privacy, or network scalability. New network models are being developed to overcome some of these challenges. NDN, a specific implementation of content-centric network, is one of these proposals. In NDN, routing and content identification are based on names instead of IP addresses. It's designed with the forwarding and routing plane separated, and the security is built into the NDN structure. Each NDN node is capable of regulating the traffic thanks to the strategic layer, which is smart and adaptive. Each NDN node is composed of three main structures: the content store, which is used to temporarily store the received content, the pending interest table, used to store the stats of each existing connectivity, and the forwarding information base, which can be populated manually or by a routing protocol, and is used to store information to build routes to the content sources. Our motivation to develop this work is as follows. Given the high mobility of nodes in VANET, which causes the link intermittency, keeping and maintaining a routing table in VANET is challenging. Therefore, many state-of-the-art solutions resort flooding. But blindly allowing nodes to rebroadcast packets in the network can escalate to a broadcast storm phenomena, where the number of rebroadcast packets can end up compromising the traffic and the network efficiency. A possible solution to this problem is to use a mechanism capable of controlling and choose specific nodes where to forward packets toward the destination. This procedure is only applicable when the geographical or positional location of the packet destination is known. To keep track of content source location, several proposals resort to frequent beacon broadcasters. For accuracy, the beacon broadcast frequency should be relatively high, but the higher is the frequency of beacon broadcast, the higher will be the traffic overhead, affecting the efficiency of the network. One of our challenges is to avoid flooding whenever possible, especially when the content source is known. A possible solution is to use FIB and store information to build routes to the content sources. However, some kind of beacon broadcast will still be necessary to keep track of the location of the content sources. To further reduce the need for frequent beacon broadcast, one hypothesis will be the use of mobility prediction. On wireless channel, nodes overhear all packets within their communication range. Then an additional solution will be the inclusion of some control information on all NDN packets. For each overhead packet, the node extract this control information and use them to refine the prediction and build the neighborhood list before the packet is possibly discarded. Given that VANET can be a very large and partitioned network, for instance, the rural and the urban environment, and it is used for various applications, for instance, the safety and emergency or entertainment application, which have different routing requirements, then a context-aware solution will be desirable. Survey the NDN-based state-of-the-art solution are not context-aware and do not include mobility prediction to reduce the need for constant beacon broadcast. In addition, the existing proposals send special hello messages for neighborhood tracking instead of taking advantage of the overhead packets in the network. Therefore, we propose this context-aware routing protocol and a forwarding strategy, which in fact is under development. The proposals also use the in-network caching for routing decisions. Now we present the main characteristics of our design. Routing protocol populates FIB with information to build routes toward the content sources. In this proposal, FIB is extended to include additional information about the node mobility, as you can see in this figure that shows the node mobility stats information that is included into the next class, alongside the face and the cost of possible hop. Content source are mobile nodes, so we enhance the routing protocol with long-term mobility prediction. This algorithm is deployed only on static nodes due to its computational complexity for mobile nodes. But this algorithm is not presented here, it's for future work. The proposed protocol further avoids beacon broadcast by leveraging the overhead packets to extract location information to build the neighborhood list. As referred before, the NDN packet are extended to include this additional information. The forwarding strategy, it uses route information from FIB. It also uses the geographical location of a content source, also from FIB, to choose adequate neighbor relay for forwarding. Neighbors are mobile nodes, and the model we propose here should avoid beacon broadcast. Therefore, we use the short-term mobility prediction to track and update the current location of a neighbor instead of using frequent beacon broadcast. Considering that the storage is not constrained in VANET, we also leverage the in-network caching. The model we propose is context-aware. It differentiates the processing of each class of VANET application. So this model caches all received data except the data for emergency application and other application with short-lived content. PIT is also extended here and to include the node ID as we can see here in the figure. For this, we use the MAC address for the installed phases. Periodically, the RSU broadcasts a special packet to query new content sources. In response to this special packet, the content source send a data packet announcing their content and include in this packet a list of their cached content. And every intermediate node forwarding this packet toward the RSU includes its own list of cached content. To accommodate the included modification in NDN and adapt the model for ad hoc network, a link adaptation layer is developed, and its main role is to build and track neighborhood and attach the node mobility stats information to all outgoing packets. About the content discovery process. The content discovery process takes place differently for urban and rural environments. For urban environment, the process is continuous. The RSU broadcast periodic beacons. The frequency of these broadcasts are being evaluated by simulation and will be fixed accordingly. Content source respond with a special packet that includes the prefix to announce and the list of all cached content, as we referred before. And every intermediate node forwarding this packet toward the RSU includes its own list of cached content. This way, all the nodes along the forwarding path are aware of the cached content of other nodes in this process. Only nodes in this path can share this list. This is the only packet that is modified by the intermediate nodes. And for security and integrity reasons, all nodes that copies and modifies this packet, then they encapsulate the previous security and authenticity information, and they sign the new copy before forwarding it downstream. For rural and the highways, we consider that the stat infrastructures are scarce or even inexistent in this environment. So the producers announce their new prefixes immediately. And in addition, a timer is fixed to 3 times the periodicity of RSU broadcast. Then when this time elapses, the content source announce their prefixes. All in all, when no correspondent fib entry is found in a given node and the request's content is not listed in the cached content table, then a broadcast takes place to locate the content sources. Now we present our summary and the discussions of our contributions. The model we propose here is under development using NDN SIM and SUM and evaluated by means of simulations. The simulations results are statically analyzing using the MATLAB or R environment. The main modification to NDN structures are the inclusion of link adaptation layer, and then the added fields in the fib and the pit for lay, selection, and mobility prediction. And we expect an overall improved performance of VANET at a cost of an increased computational overhead due to the processing all overhead packets. And we include here the overhead, the computational overhead that we will have on computing the mobility prediction. Thank you.